Alright guys, weather's kind of nasty today, so we're going to try to make this one a little bit shorter than yesterday's plate boundaries lecture. Today's topic, hotspots, hotspot volcanoes. Maybe you've heard of these, maybe you haven't, but it's really one of the coolest and I think one of the easiest ways to grasp how all this plate tectonic stuff, some really solid evidence that almost anybody can wrap their brains around. that you know, in say the 1970s, maybe 60s, plate tectonic movement really picks up, and in the 1970s, all of a sudden, geologists have this shiny new tool that they can use to explain everything. And hotspot volcanoes are one of the things that we really got a good explanation for because of plate tectonics. So I said volcanoes. I said that word volcanoes. Yesterday we learned about plate boundaries, and we found places on Earth where we could get volcanoes, subduction zones, right? Whether it was oceanic and continental crust coming together, forming a continental volcano arc, like we have here in the Pacific Northwest, Mount Rainier, Mount St. Helens, etc. Or maybe it's oceanic crust coming together, one of them subducts beneath the other, and we get island arc volcanism. The Aleutian Islands, the very tip of Alaska, that part of Alaska that goes out like that, island arc volcanoes. And most volcanoes on Earth are related to subduction, ocean trench, the water, all of that. Not hotspot volcanoes. These are different. We're going to go to two places in the United States. If I was better at video editing and stuff, I'd put in a bunch of fancy pictures from Google Earth, but you're going to have to get on Google Earth yourself and go look at these places, because I don't know how to do that video editing business. Anyways, you might know where we're going. You might know where the topics are. Maybe you've even heard of hotspot volcanoes before. If so, that's great. We're going to two places, Hawaii, out in the middle of the Pacific Ocean, and Yellowstone National Park. It was a destination for my very first big family road trip. All five of us piled in the pickup and we drove out to Yellowstone, camped there for a few days. It was awesome. If you ever get a chance to go to Yellowstone, take it, because it's really cool. But first we're going to go to Hawaii. We're going to gather some evidence. We're going to go to Yellowstone. We're going to gather some evidence. We're going to put it all together, because that's how science works. Okay, so we're going to start off with Hawaii. You could probably picture what Hawaii looks like, but in case you can't picture what Hawaii looks like, here it is. I drew a little map for you. There's 7 or 8 islands here. 1, 2, 3, 4, 5, 6, 7, 8 that I drew. I copied that off Google Earth. This is a map, so I should probably put that on there. North, right? We always need an orientation with our maps. So we've got 8 islands. There's a couple other smaller ones that aren't on the map, but we got 8 main islands. And they're all kind of in a line. Wouldn't you say? It's windy out here. Sorry about that. Wouldn't you say that's kind of a line from the southeast up to the northwest? I would too. So we've got these islands in a line, and one thing we might notice too, in the southeast, that's our biggest island. If you can see that, I need to get myself a clipboard or something. Biggest island in the southeast, and they basically get smaller going to the northwest. You'll notice I put a star down here. That is Kilauea. Kilauea is the active volcanic vent on the big island of Hawaii. That volcano, that island, is growing today. There's lava erupting from that vent right now. and that island is still growing. So, you know, we know about how geologists can get ages on stuff. Let's give an age to the big island of Hawaii. We'll call it 0 million years. 0 million years, because it's still forming today. 0 million years. And if you've ever been to Hawaii, if you've ever been to some of the different islands in Hawaii, one of the things that stands out is that the islands look different. There are all these islands, you know, hundreds, couple thousand miles from anywhere, out in the middle of the Pacific Ocean, but they all look different. The big island of Hawaii is kind of jagged, and there's a lot of rock and stuff. If you go up here, this one is Kauai. If you go up to there, it's like lush jungle, and there's canyons, and it's a smaller island. Doesn't have as much elevation. It looks like it's more eroded, and the reason it looks like it's more eroded is because it is more eroded. And if we were to get some ages on those rocks, I should mention Hawaiian Islands, nothing but basalt. Those islands sprung up off the ocean floor. They're basalt lava rock. The whole island's built out of basalt. As we go from southeast to northwest in the Hawaiian Islands, they get older. Maui, 0.8 million years old. Molokai up here, 1.8 million years old. Oahu is 3.7. And up here, Kauai, 5 million years old. So check it out. The further away we get from the big island, the older those islands get. So they're getting older, but they're also getting more eroded. And that makes sense, right? If they've been around for 5 million years, they're going to have more time to get eroded. This one's still building down here. Okay. So what do we have here? Do we have some arc volcanoes? We got volcanoes coming up off the ocean floor, and we got ocean on both sides of them. It's kind of in a line. That's what we said, arc volcanoes form in a line. But no, these aren't arc volcanoes. And in fact, it's more than just this 5 million year history. It's more than just this 5 million year history, because under the water, going off to the northwest, are what are called seamounts. Seamounts. Seamounts are simply underwater mountains. Makes sense, right? Seamount, underwater mountain. Yeah, cool. And those seamounts march off across the ocean floor to the northwest, and I'll show you this diagram. It's page 25 in your yellow book. If you got your yellow book, here it is. We've got seamounts marching across the ocean floor back to the northwest, making almost a perfectly straight line, dating back 43 million years, and then that line changes direction, and it heads up to the north, and we have a continuous line of seamounts ending today at the Hawaiian Islands, going back 70 million years. And that northward point is all the way up, right next, snuggled up to Siberia. When you're done watching this, go open Google Earth and go look at the Hawaiian Island and the Emperor Seamount chain. Okay, we're going to pause that for a minute. There's some evidence from Hawaii. Do we know what it means yet? Maybe you do. Maybe you're a couple of steps ahead of me. Maybe you've heard about this before. Or maybe not. Anyways, to make it clear, those volcanoes, the Hawaiian volcanoes, Kilauea today is springing up out of the middle of the tectonic plate. We are nowhere near a plate boundary. Not a convergent, not a divergent, not a transform plate boundary anywhere for 1,000 miles in any direction. All right, now we're gonna go to Yellowstone National Park. Put a big star there, kind of like I did on Kilauea. I put a big star on Yellowstone National Park. Now, Yellowstone, you got Old Faithful, you got geysers and hot springs all over the place. It's called Yellowstone because the rock's all covered in sulfur. There's rocks that are made of nothing but sulfur. And it's got a yellow color. It stinks like rotten eggs. There's also a lot of beauty there. But Yellowstone, the park itself, sits in this big hole in the ground. It's a big hole. It's like 30 miles across. And that big hole is a volcanic crater. Yellowstone National Park is a volcano. It's a volcano in the middle of the North American tectonic plate. Not a plate boundary for miles. And so just like we can do with Hawaii, where we can go to each Hawaiian island, we can collect some basalt lava rock, and we can take it to the lab and we can get a date on it, and we can get an age for it. We can do the same thing at Yellowstone. In the Yellowstone crater, in that big crater that's called a caldera, I should write that for you. It's the first time maybe you're hearing it, but it certainly won't be the last time. Yellowstone caldera. We can gather rocks, volcanic rocks. It's all volcanic rocks there. We can gather that volcanic rock and we can take it to the lab and we can get a date. And the date for that big hole in the ground in Yellowstone National Park, the date for that is 640,000 years. 640,000 years. Or, if you prefer, 0.64 million years ago. Again, sorry, I'm not holding these up here for very long, but you can pause the video. And I'm starting to get cold, so I want to get through this pretty quick. So, that's our big hole in the ground. That's the Yellowstone caldera. But just like Hawaii, where we have these seamounts marching off in a line to the northwest, if we zoom out from Yellowstone, you can see these in Google Earth too. It's your assignment. When you're done getting your notes organized, I want you to go to Google Earth, look at the seamounts on the ocean floor of Hawaii, near Hawaii, and then I want you to go look at Yellowstone, and then you're going to look to the southwest of Yellowstone. Yellowstone's right here on the boundary between Montana and Wyoming and Idaho. And you're going to look to the southwest. And what's it next to? It's, I think, just northwest of Post Falls, Idaho. And then marching off all the way across in sort of a U shape across southern Idaho are other old holes in the ground. Other calderas. Older calderas. We can do the same thing that we did with Hawaii. And we can get dates from those volcanic rocks in the older calderas. We got 0.6 million years for the current one. The one before that, 1.2 million years. 1.8 million years. 2.4. Marching off down in a pattern, creating a little U shape right all the way across southern Idaho. Now there's a bunch of people farming out there. But each of those is a caldera. Each of those is a Yellowstone volcano. And they're pretty much in a line. Okay, what do we got here? We got two completely different tectonic settings. Well, no. We've got a similar tectonic setting in that it's right in the middle of a plate. But one's on the ocean floor, one's on a continent. Is there anything else that we got in common? We've got a line of old volcanoes that ends at an active volcano. Wait, Yellowstone's active? Hell yeah, Yellowstone is active. Yellowstone is an active volcano. Kilauea is an active volcano back in Hawaii. So, I guess I can't hold it anymore. These are the result of the same process. They appear very different because of the different type of crust. Ocean crust versus continental crust in Yellowstone, ocean crust in Hawaii. Different crust, but the same process. Both Hawaii and Yellowstone are sitting on top of what we call a mantle hotspot. These aren't the only two hotspots in the world. There's 20 to 30 of them. I can't remember the exact number. They're all around the world. And let's see if we can try to visualize this. And I got page 26 in your yellow book has a nice diagram. But what we want to think about is we want to think about these hotspots as being like a vent, sort of a vent where heat escapes the core of the earth. You got heat tremendously hot in the core of the earth, and in certain spots, most of the earth, you think of it as being kind of insulated and held in, but there are certain spots where that heat escapes and it all flows out in the same spot. And we want to think of that heat as coming from deep within the earth, it's not in the lithosphere, and it's not even in the asthenosphere. We want to think of that heat as coming from deep within the earth, and what it does is it causes melting. It causes melting in the lithosphere that we remember our tectonic plates are these chunks of lithosphere. And so we've got a source of heat, and we've got a tectonic plate that's moving across it. And whatever part of that tectonic plate is above the source of heat is a volcano. And this is a little controversial, but most geologists will tell you that hotspots are stationary. Hotspots aren't moving. What's our evidence for that? Well, how about this? How about this for our evidence for that? How about this big straight line with a hotspot right here? There. Put a star in my yellow book where the hotspot is. And as the Pacific plate, the tectonic plate, as that big slab of lithosphere moves across our hotspot's staying in the same place. And it's kind of like a conveyor belt in a factory. And whatever's over that hotspot, the hotspot makes a volcano there. Here's a nice diagram of our Hawaiian hotspot. If you had your yellow book, there's a couple of little things. What is this boundary? What direction? What direction? What you want to see here is the Pacific plate moving from right to left across the page, and that hotspot is staying in the same spot. And as the hotspot moves, or as the plate moves, the location of a new volcano a new volcano appears over the top of the hotspot. Then over here in this diagram, you might notice I included an underwater volcano. It hasn't broken the surface of the ocean yet. I can't remember the name for this volcano, but if you go on Google Earth and you look at Hawaii, look on the ocean floor to the southeast of the big island of Hawaii, and you will see that underwater volcano, that next Hawaiian island forming deep under the ocean. Couple last ideas, couple last thoughts. Sometimes we'll refer to hotspots as mantle plumes. They're plumes of heat. A plume, like a big column of heat coming from deep within the mantle. We might call them mantle plumes sometimes. Mantle plumes and hotspots, so it's mean exactly the same thing. And the thing I really like about these two examples and what hotspots do for us is they make it crystal clear what direction a plate is moving. And especially with the Hawaiian Islands and the Hawaiian Seamount and the Emperor Seamount, it makes it really, really easy for us to reconstruct the rate that the Pacific Plate has been moving for the past 70 million years. If we assume that hotspot stayed in the same place, we can use the age of those mountains and the distance of those seamounts, not mountains, seamounts, the distance of those seamounts to the hotspot, and we can calculate a rate. We're not going to do that right here, but it makes it really clear. So what direction are those two plates moving? We talked about two hotspots underneath two different plates. The Pacific Plate underneath Hawaii and the Hawaiian hotspot. That plate is moving to the northwest. That plate is moving to the northwest. And as the plate moves and the hotspot doesn't, a new volcano shows up on the southeast of that line. So what does that mean for Yellowstone here? What's that mean for Yellowstone? Has the North American plate always been moving in the same direction? Has it been moving the same way like the Pacific Plate has? No, it hasn't. We can tell because this has changed direction. There's a curve to this line of calderas. But we can look at the most recent part of it. What direction is that? It's from northeast to southwest. So what direction is the North American plate moving? Well, this is at the end, the Yellowstone is at the end of the North American, of this line of calderas. So the North American plate right now has to be moving to the southwest. North American plate moving southwest. Southwest motion on the North American plate. Northwest motion on the Hawaiian hotspot. And then I wasn't planning on doing this, but I want to leave you with something hopefully to blow your mind a little bit. One last thought about Yellowstone. We're going to talk more about Yellowstone here in a few lectures. Sorry, it's Sharp is kind of soaking through on the back of this. Most recent Yellowstone eruption, 640,000 years ago, 0.64 million. Before that, 1.2 million. Before that, 1.8 million. Before that, 2.4 million. Before that, 3.0 million. See a pattern? On average, the Yellowstone caldera erupts every 600,000 years, or 0.6 million years. So if you want to be freaked out about something, be freaked out that we're 40,000 years overdue for a Yellowstone eruption from the Yellowstone hotspot in the middle of the North American plate. Alright guys, I'm going to get this one posted to YouTube. I'm going to get you guys a revised schedule so you know exactly what to expect. That's coming in the next day or so. And also, quiz number 2. We're going to try to figure out how to do quiz number 2. I'm going to have to send it to you and have you send it back to me or something. We'll get it figured out. Hey, we're resilient. Until next time, so long from Ellensburg.